Hello everybody, this is week 8 and we will continue talking about the variation of flow depths in an open channel when the flow is experiencing a hump on the bottom. Okay, so you may remember that in the in week 7, the last Thursday, I solved one problem which was the case of a subcritical flow, and the upflow flow was not changing. Today I will continue to explain the topic, and I'm going to solve you one more problem. But first I have to explain all the cases in a clearer way. You have already know the concept. Okay, just let me again show you the energy graph. Okay, you know that I was using this energy graph, specific energy graph, to explain the situation. In the case we handled on last Thursday was a subcritical flow experiencing a hump on the channel bottom. Then while the flow is passing over that hump, if it's subcritical flow, we learned that the depth of the flow is going to go down. It will decrease. Okay, it will decrease until the point of reaching critical flow depth. Okay, so this was the first case, and I told you that there are 4 possible cases actually, and I solved one problem just focusing on this particular problem, and today I will explain you the further details about the other possible cases. Okay, let's have a look at this 2 graphs. It is actually another presentation of the flow depth versus the hump height. So I like this graph because it explains in a better way that how the depths are changing, so you can easily follow in both flow types like subcritical and supercritical flows. So let's focus on the first one. It's going to be a kind of reminder for you for the last course, and then I will focus on the second one, the supercritical flow today. So let's have a look at that, what we have. Okay, this is the starting point of the flow. Okay, and look at that. This is the x-axis here is representing the height of the hump. So if the height of the hump is 0, the flow will continue as this. So there will be no changings. But if you add a kind of hump with a certain height, like theta z, then your original flow will continue as it is. Upflow. Okay, upstream flow. Upstream flow will continue as it is, but the downstream flow you will have a lower depth, as you learned in our earlier problem in this case. Okay, so y1 is bigger than y2. Have a look at this energy graph. You will understand exactly what I mean. This is the first case, and this is the second case. This is the first point, this is the second point. And when you have experienced a hump with delta z height, the depth of the water is going down, okay, on the hump. It is subcritical flow. Okay, let's continue on this graph again. And this depth will increase if you keep increasing the height of the hump. And at a certain point, you are going to reach the critical depth. And as you remember that on Tuesday, two lectures ago, I explained that if water passing over a broad crest, okay, you are going to have critical depth on the crest. Okay, so this is the case what you will have. There will be a depth of water stabilized, and it is not going to be no more lower than critical depth. So the thing is that if a subcritical depth is approaching a hump, and if it passes over that hump, you are going to have a depth which cannot be shorter, again, cannot be smaller, okay? Cannot be smaller than the critical depth. Okay, this is the case what we have. And this is very interesting point. And if you reach that part, then you are going to see that the downstream flow will continue at the height of critical depth, but you keep increasing the hump, I mean the obstacle on the bottom, then what you are going to experience that the water is going to bounce back at this certain level, and you will experience a kind of rising up on the upstream flow. Okay, so the closer point to the flow, okay, a closer point to the flow approaching the hump will be higher than the original height on the original depth. This is an interesting case. I will explain. Okay, let's continue in this graph. Okay, this is much better. I just provided some illustration. I mean, I just wrote those illustrations today to explain you the case in a better way. Let's have a look at what it tells us. This is the case. Subcritical flow is approaching the hump, and the delta Z is not as large as to get the depth of water on the hump is critical depth. So it is passing as subcritical flow. And this is the case one. I mean, this side of the flow. And at exactly this side, when the height, water depth on the hump is equal to critical depth, then you are going to have a kind of flow as this again. And this is just turning point into the third case. In the third case, there is no way that the depth of the water on the hump cannot be, I mean, there is no way that this depth on the hump cannot be lower than critical depth, okay? So what we are going to have, we are going to have a kind of bouncing back effect, as you see on the figure, and the water will rise up. So in order to solve such problems, guys, the thing is that what you should, first you should calculate the critical depth in both sides. I mean, in upstream flow and downstream flow. And after calculating the critical depths in both sides, okay, you will check that if the water is passing subcritical or not. And if it is passing a subcritical flow, then you are going to decide what should we have. And if the depth of water on the hump is equal to critical depth, then you will assume that there will be bouncing back effect, and you should calculate again the new height on the original flow, okay, in the upstream flow. So it is going to be another calculation you should perform. You should also calculate the new depth with rise on the upstream flow. Okay, this is the case for subcritical flow, and this is the case for supercritical flow. Okay, if we have supercritical flow, we see that this is the energy graph. Actually, these are the depth profiles against the hump height. And in the first case, the depth on the upstream flow is constant. Okay, it goes constant until you are reaching the critical depth. Okay, you see that it is totally the opposite. Y2 is always higher than Y1. Okay, it's always higher than Y1 for supercritical flow. But when you reach the critical depth on the weir, there is no way that a weir can hold more than, okay, more than a water height, which is more than critical depth. Then the velocity will increase on the upfront flow, upstream flow. Then you are going to have a kind of falling down in the original flow. So you should calculate the new depth in the upstream flow. So this is the case for case 3 as given on the figure. Okay, so what we have in that type of problems, I solved this typical problem for you, case 1. Case 2 is actually just to explain you what is going to happen when you reach the critical flow. And case 3 is the second alternative, that if the flow is, if the height of the weir is larger than the critical depth, then you are going to have, I mean, reaching the critical depth, then you are going to have second case. So case 1, case 2 are the possible question types, and this is here case 3, and this is here case 4. You might have 4 different questions in this in this section in your exams or in engineering designs. So you should learn, and you should be able to solve all those type of questions. Just try to understand what I'm telling you. Okay, this is the theoretical part. Now I am going to solve you one more problem. Then I will pass to next topic on Thursday. So lecture will be over for today. Guys, do you have any questions on these cases? Is everything clear for you, or is there any question you'd like to ask? Please Ask me now, and I will be happy.
May I ask?
Again. Okay, Akdana, please go on.
So in this slide, the second and the third pictures are like one case, right? When the second height is equal to critical flow.
Actually, this second case is just a kind of presentation to show you that you are reaching exactly this point, okay? Follow my cursor, okay? So you have a kind of data set, which is exact value to reach critical flow, okay? On the right side. It is just making a kind of presentation for us. But after this point, have a look at, after this point, you are going to have case 3. Did you get it?
Yes.
Okay, so 1 is this, second is at just point, this point, and 3 is this point. Any other questions, please? Okay, let me solve one problem, and I hope that you will understand in a better way. But again, guys, this is a little bit tough topic, and the next topic, I mean, on the next time, I am going to cover another topic. Now you just see that we are adding a hump, but next time we are going to make a kind of, we are going to have a narrow or like contraction or expansion on the channel, okay, in terms of width. So it is going to be another case you should handle. So you will see that it is a little bit different than what we are doing now, and you are going to learn all possible cases if a water channel experiences differences in the cross section and how the water flow is going to behave in a different way. These are the cases you should learn, and you are supposed to answer in a question in this regard. Okay, so let's have a look at this problem and solve it. So this problem is basically telling us that there's a rectangular channel and it is 2.5 meters wide. Okay, so the width of the channel is constant through all the flow, and it carries the flow of 6 cubic meters per second. And the original depth, not original depth, the upstream depth is 0.5 meters. Okay, so this is the case it is given. And it is asking us that calculate the height of a flat topped hump required to replace a section to cause critical flow. So it is asking us that what should be the height of this hump to have exactly this condition, case 2 or case 3, because we don't know at the moment if it is subcritical or supercritical, but I like to give you a sneak peek. This problem is a supercritical problem. So this is the case, okay? This is the case, but anyway, we are going to confirm. We are going to calculate the Freud number, and then we will check it out that if the flow, upstream flow is supercritical or subcritical. So it's going to be supercritical, guys. So this is the exact case what we are looking for. Akdana, I think this is also an answer for your case, because you told me that what it represents, this case 2 in each figure is representing us that exactly this, the exact height giving us the critical flow, okay, for the channel. So this problem is just focusing on that particular position. But there is one more additional information here. It says that there is energy loss, okay? I mean, of course, there are energy losses in everywhere, in every kind of flow. And now we are going to consider it. And it simply says that the energy cost created by the hump is 0.1 times, it means 10% of upstream velocity head. So you are going to calculate here velocity head. And do you remember that? What is velocity head? Anybody can answer this, please, quickly? What is the velocity head on the upstream flow?
You mean the formula?
No, what is the velocity head on the upstream flow? Velocity head. Velocity square over 2g, right? Velocity square over 2g is the velocity head. You remember that potential head, velocity head? And
yes.
Yeah, these are the heads what we have. So velocity head is velocity square over 2g. So this is the velocity head. Simply, you will calculate the velocity here. And then you are going to calculate velocity square over 2g. Then you are going to multiply with this 0.1. Then you will get the loss, energy loss. Okay, this is going to be our energy loss. I think it's clear. So let's solve the problem. The first thing is, first, you should check the flow regime. I mean, if it's critical flow or subcritical flow, it's quite easy. And we know the equation for how to calculate the Freud number. And please do not forget that while you are calculating Freud numbers, don't forget that 1 and 2. Those 1 and 2s are indicating that the location of the flow. 1 means upstream flow, 2 is downstream flow, and here the upstream flow, the Froude number for upstream flow, and there will be different Froude numbers for both cases, is equal to velocity over in root square, I mean gy1, and it's simple. You can easily calculate because I already calculated here what is the velocity. Velocity is flow rate over area, and we have a kind of velocity over here, okay, like 4.8 meter per second. And exactly, we don't know what is the velocity on the right side, and the velocity on the right side can be also calculated by if you knew that what is the depth of the flow on the right side. But we know that for this particular case, the depth of the flow on the right side should be equal to critical depth, because the question is just asking for us to focus on these critical flow conditions. And Froude number is 2.17. It is larger than 1. It is supercritical, okay, as I told you that. So this problem is a kind of supercritical problem. So let's say that flow is passing over this hump as a supercritical flow. This height, or let's say this depth, 0.5, should be shorter than y2. Y2 will always be larger than y1, and the maximum height you can get on the right side is the critical depth. So this is asking us that what should be the maximum height you can get it's critical depth. Okay, and then here I wrote for you the energy equation, specific energy for point 1. It is written on the screen, please check it out. And we have the depth here 0.5, and this is the velocity head. Okay, so totally we have 1.67 meters of total energy on the left side, on the upstream flow. And as you remember, the downstream flow energy, specific energy on the downstream flow should equal to upstream flow energy minus theta z. Also, I'd like to add you something here. If you have energy loss, you should also subtract it on the right side, okay? So you are supposed to add it here as a minus energy loss. Then we have 1.67 minus theta z minus energy loss, okay? Minus energy loss. Let's calculate the energy loss. And the energy loss here is equal to 0.1 times velocity head on the upstream flow. It is 0.12 meters. It's quite simple, actually. You can easily calculate it. And now we know that what is specific energy at point 1. We know the energy loss. We don't know what is theta z. It is supposed to be calculated. And also, okay, and also we don't know what is the energy at the point 2. So there are 2 unknowns. In order to solve this problem, we have to go and calculate the possible energy, what we have. And I like to show you this graph again. Let's go and check this graph to help you guys. Okay, look at that. We are talking about exactly this point. Just okay, follow my cursor. We are talking exactly this point, and this is point 1. What we have. This is supercritical flow. This is point 2. This is supercritical flow again. But this point 2 is going to get exactly here. Okay, so we will have our point here. Point 2 is here. This is our case. And if you look at here, you will see that this is critical depth versus minimum energy. And as you may easily remember that in earlier parts of the lecture, I think it is 2 or 3 weeks ago, I explained to that the energy at that point is equal to 1.5 critical depth. Okay, so let's calculate the critical depth on the right side. It is easy to calculate. You have those equations, and if you calculate it, you are going to see that the critical depth is going to be 0.84. And let's check it out that if this 0.84 is larger than 0.5, yes, it is larger than 0.5. This is correct. So water is going to go over hump by a higher depth than the original flow, okay? Because it's supercritical flow, that will be rising up on the right side. And the total energy at this point should equal to minimum energy of the system on the right side. And minimum energy means that 1.5 y critical, okay? So if you calculate it, you are going to end up with this number, okay? You are going to end up with this number. Sorry, I mean, this is y critical, and just multiply it 1.5, then you will find it. And this critical energy is going to be, it will be equal to specific energy of on the right side. And then by using this equation, it is quite simple. we can find what should be the velocity at the right side, and the velocity on the right side should be equal to 2.87 meter per second. Okay, so actually this velocity is not necessarily, I mean, this is not asked. You should not calculate it. I mean, this part is not required actually, because after calculating the critical depth, you can put this 0.84 here and multiply it 1.5. Actually, there is one missing here. I am going to add it, guys. Just my mistake. Let me add here 1.5. Okay. Yes, correct. This is 1.5. This is 1.5. Then you are going to end up. I am not pretty sure at the moment if the calculation is correct. Could you please quickly check that this calculation is correct? I don't expect that I made a mistake. Let me calculate it again for you. I don't expect that I made a mistake, but anyway, let me check again. 1.5 times 0.84, most probably it is just a typo, minus 167 plus 0.12. It is going to be 0.29 meters. Look, correct. There is no calculation mistake. It is typo. Okay, so you see that the height of the hump should be 0.29 meters. This is the solution of the problem. Yes. Okay. Do you need any clarification? Is it clear?
May I ask about the like the minimum critical energy?
Yes, please.
Is it always 1.5 times y critical?
Yes, exactly. This is. I mean, if you do not, I mean, if you want to be sure that, please go our earlier slides. Okay, a couple of weeks ago when I introduced open channel flow, you will see that y it is equal to E minimum. Okay, we extracted it. I mean, we calculated it in the earlier parts. And also, if you want further reference to see it, please check the Yunus Chengas book. You will see the further information there. But my answer is yes. Critical minimum energy in open channel is always equal to 1.5 critical depth. So it is simple actually. You can easily realize that why it is. If you write here, for example, instead of y2, if you write here y critical, then you are going to end up with 1.5 y critical. Okay, you can make this calculation by yourself if you want, which is easy to calculate. Okay. Any other questions, guys? So again, you are following my lectures, and I am assuming that you are following me carefully. I don't see your faces. I only see Resul. Thank you, Resul, for turning on your camera. Actually, I want all my students to turn on their camera because it is easy to see your faces while I am teaching, because I see your responses. Even it is easy to communicate if I see the faces. Thank you again, Resul. You should do you should do the same. But the thing is that no one is speaking. No one is providing. If no one provides any response, I assume that it is learned. Okay, so then I am going to close the session. Waiting for one more second for you. If you have any question, then I'm going to close the session. I will continue on next time. No questions?
It's okay.
Great. Okay, thank you guys. See you next time. And I am doing my best. I am sorry, guys. Be patient. I will mark your midterms as soon as possible. Okay. Most probably you are going to receive the feedbacks and the marks until the end of the term break. So I will work during the nervous break on the papers. The classroom is busy. It's taking too much time, and this is not the only course I'm teaching. I'm also teaching other courses. So it's a little bit difficult for me to finish everything in a short time. So just allow me, please, until the end of the spring break. Then you will get your marks and feedbacks. Okay, thank you. See you next time. Bye-bye.
Bye.